Okay. Where did it go? Is the screen visible?
Yes, sir.
Module 3 LEFM approach. Is that visible?
Yes, sir.
Okay. What is the last we learned? Fracture toughness now. This is the last one that we took. Which is the last one that we learned?
Crack length versus applied cycle.
Okay. Okay. So this is the one, no?
Yes, sir.
Yeah. So three stresses. S1 is greater than S2 greater than S3. All the specimen contained same crack length, and the number of cycles for higher stress is less. Okay. So fatigue crack growth was larger in higher stress specimens. Okay, this is what we learned. And one more you observe here, delta A by delta N. Okay, that is crack length versus number of cycles, that is applied cycles. N versus crack length. A is essentially slope of delta A by delta N. Okay, so this is what we are going to learn now. That is, by applying LEFM concepts, okay, we will be able to reduce data to a format useful in fatigue design. This involves obtaining fatigue crack growth rate data. Okay, fatigue crack growth rate is what we can get. So this is essentially delta A by delta N versus applied stress intensity factor delta K. So from where do we get delta A by delta N? Again, from the previous graph over here, we get slope as delta A by delta N. That is, the fatigue crack growth rate delta A by delta N is simply the slope of A versus N curve. That's it. Okay. At a given crack length or given number of cycles as defined by delta A by delta N. Okay. The corresponding applied intensity factor delta K is calculated knowing the crack length A, applied stress strain delta S, and stress intensity factor solution K. So we can find out delta K, okay, by taking K max minus K minimum, that is equal to S max root pi into A into alpha minus. So this we have learnt in the previous classes, if you remember. Okay. Right. So here we have taken stress intensity factor to be equal to, okay, can you remember? Here we learned the stress intensity factor K to be equal to S into root pi into A, where S is the stress and then A is crack length. So we have learned it previously. So same thing is applied here. That is, to come back to this discussion over here. Okay, so this is S max, because for K max we need S max into root pi into A into alpha minus S minimum root pi into A into alpha. So pi A alpha is common, so take out that. S max minus S minimum into root pi into A into alpha will give you the value of delta K. Is that okay? Somebody is waiting. Okay, admit. Okay, could you understand what we are discussing? So we can apply, okay, LEFM concept. We apply LEFM concept, okay, to get to do fatigue design. So for this, what we need is the crack growth rate delta A by delta N and versus the applied okay, stress intensity factor delta K. Delta K we can obtain using equation here. Okay, that is S max minus S minimum into root pi into A into alpha, whereas delta A by delta N is simply the slope, okay, of the stress, the crack length versus number of cycles in the sketch that we have taken over here, crack length versus applied cycle. Take the slope, delta A by delta N is what you are going to get. So this versus stress intensity factor delta K, this factor range delta K will give you the fatigue design. It will help you for fatigue design. Is that okay? Fine. Are you there?
Yes, sir.
Yes, sir.
Okay. Next. Of course, LEFM can aid both qualitatively and quantitatively because it will give you the exact quantity of crack growth, and that will help us in estimating the static strength, fatigue crack growth life, and final fracture. So the stress intensity factor describes the stress field at the tip of a fatigue crack. This is what finally conclusion can be made. Is it okay? That is, I'll go back to a little bit, I'll go back and we'll rework. We learned about fracture toughness. Essentially, toughness is in the plastic range. Okay. So more the ductility, more is the toughness. Okay. So ductile material will have more toughness. So when we call fracture toughness, if you have a fracture already, crack already present in the member, then we call it as fracture toughness, right? So that is essentially is a measure given by the critical stress intensity factor Kc, which is given by SC root pi into AC. And then fracture toughness is a quantitative way of expressing material's resistance to crack propagation. So it is essentially related to crack propagation. Okay. Next, we learned about the influence of thickness, okay, on crack growth and stress intensity factor and fracture toughness. And here we've learned that fracture toughness is the energy absorbed by the material with the presence of crack. So there is some optimal value of thickness beyond which even if you apply, there is not going to be, or it does not alter fracture surface appearance, or it does not alter or decrease the fracture toughness. This is what we learned. And then fracture toughness can be very sensitive. So fracture toughness depends upon various parameters such as grain orientation, chemistry, microstructure. Then we learned it is blunting, irregular crack front, change in or mode of crack extension, or it also depends on branching. Again, fracture toughness again depends upon temperature, strain rate, and corrosive environment. So totally 3 plus 3 plus 4, 6 factors on which will influence the fracture toughness of the material. This is what we learned. Then we learned about path of crack during fracture. Okay, is controlled by microstructure. The dominant constants being precipitates, grain size, and texturing. These three can control the crack path of crack. Okay. Then we learned about influence of fracture toughness. Then fatigue crack growth rate delta A by delta N and delta K. So this is what we learned today also. So delta A by delta N is the slope. Delta K is stress intensity factor range. Correct? Okay. So for learning this fatigue crack growth delta A by delta N to delta K. Okay. We have taken this sketch, which is essentially a graph between crack length versus applied cycles. So this indicate we have taken a material specimens, 3 specimens of same initial crack length, subjected to different stresses of increasing order. Okay, and we observed that the number of cycles that a component can go is less as the stress is more. The number of cycles that can be applied to material is lesser and lesser. And also, this delta A by delta N is essentially the slope. Okay, so that's what we learned over here. Fatigue crack growth rate delta A by delta N versus stress intensity factor range delta K. Okay, so this involves obtaining these two parameters in fatigue design. So for fatigue design, we need delta A by delta N versus stress intensity factor range delta K. So delta A by delta N we can obtain from the graph because it's essentially slope of the A versus N. Okay, but how do I get delta K, which is stress intensity factor range delta K? So that we can know by knowing the crack length A and applied stress range delta S and stress intensity factor K. Okay, so that is essentially S max minus S minimum root pi into A into alpha. A is crack length, S max is maximum stress, S minimum is minimum stress. Is that okay? Are you there? Now,
Yes, sir.
what you do is just note down this equation here. Just note down this equation. Finished, huh? Finished?
Yes, sir.
Okay. And then so this is what final conclusion is that what we learned. Okay. So next, in module 3, okay. So we have second part of module 3. So up to LEFM approach we just finished. So we have notches and their effects, concentration and gradients. So this is the next what we need to learn. Okay. So essentially notches and their effects is what we need to learn now. Now, so again, we come back to discussion on notches. So notches, for all discontinuities, they call it as notches. Either it's hole, fillet, chamfer, or it can be presence of hole or stepped shaft or sudden decrease in geometry. All these things are called as notches, and these notches cannot be avoided in many structures and machines because we need to drill, put bolt, and all those things. So notches will be present definitely, okay, in all the components that we use. So a bolt basically has notch in the thread roots, okay, and at the transition between head and shank. So this is the head, for example, and this is the shank, okay. So this is the shank of a bolt. Okay, suddenly there is going to be decrease in diameter. So that's going to be the presence of a notch. Then we have rivet holes. So to do riveting, we need to make holes in the sheets before riveting. Then again, welds on plates, they will give rise to presence of notches, cracks, then keyways and shafts. These are all notches, okay? And these notches can be dangerous if not controlled properly, okay? So say suppose if you take a plate, then plate with a hole, so the hole is also a type of notch, okay? So around the hole we have seen in our finite element analysis that around the hole you have got maximum stress, correct? Similarly, when you have stepped shaft like this or when you have grooves present, keyways present, they all act as notches. Okay. Now, to understand the effect of notches and means to overcome them, one must consider five parameters. What are those five parameters? One is concentrations of stress and strain. Second one is stress gradients, mean stress effects and residual stresses, local yielding, and nucleation and growth of cracks. These are the five parameters, okay, one must consider to overcome the effects of notches. Is that okay? So notches are inevitable, but these notches are also dangerous if not treated. So to understand the effects of notches and to overcome them, we need to understand the five parameters. Is that okay? So these five parameters are stress concentrations, stress gradients, that is, what are the various maximum to minimum value stresses, mean stress effects, and residual stresses. That is, residual stresses will come during manufacturing or processing. Then local yielding near the presence of notch, okay, and nucleation and growth of cracks. That is crack nucleation and crack propagation. Is it okay? Could you understand what is notch? What is its required? Hmm?
Yes, sir.
Fine. So now what you do is please note down this complete sentence. So without notch, we cannot design the components. So notches are inevitable, but it should be treated also in a better way. So to understand the effect of notches, we need to have these five parameters in mind. Finished, huh? Finished?
Yes, sir.
Yes, sir.
Okay. So now, so what are these concentration of stress and gradients of stress is all about? So that is, this is what we are trying to learn, concentration of stress and stress gradients. So first two things is what we are trying to learn out here. So the notch concentrates stresses and stress. So this is obviously we know. So if you have a plate, okay, with a hole, this we have seen in our labs also. So when you have hole, so the presence of this hole, okay, will have the stress rises. That means it will enhance the presence of stresses, or there is going to be concentration of stresses and strains around this hole. That is essentially called notch. Do you agree with me? Do you agree with me? Yeah?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So the degree of concentration is a factor of fatigue strength in of notched parts. So it is measured by elastic stress concentration factor. So we have learned in our engineering that the stress concentration factor is the ratio of maximum stress to nominal stress. That is, K is equal to, okay, what is that we have learned? Sigma max divided by what? Divided by sigma nominal. Correct? This is what we have learnt in our undergraduation also. That is, stress concentration factor is the ratio of maximum stress to nominal stress. Is that okay? So that's the learning about concentration of stress. Next, coming to plate with the whole case again. So KT depends on the ratio of hole diameter to sheet width. Why it is so? So please remember in DME1 we have done many such problems where we take A by W ratio, correct? A is the diameter of the hole, W is the width of the plate, correct? So depending upon the A by W ratio, so there used to be a curve something like this, correct? There used to be a curve like this in your data handbook. Do you remember? Anyone remember this?
Yes, sir.
Yes, sir.
Okay. So we used to find out A by W, then come to A by W, then look for this curve, and then travel leftwards to get the value of what? To get the value of stress concentration factor KT. Is that okay? You remember?
Yes, sir.
Okay. I hope you will remember this. So in the upper curve, nominal stress is defined. So this is the nominal stress curve. In the lower curve, nominal stress defined, that is load versus net area of remaining after hole has been cut out. Okay, so that means before presence of hole here, this curve represents after the removal of area. That's why you have got W minus A into T. This will give you effective area. Effective area is this edge portion, this plus this areas, correct? That will give you the effective area. Okay, so that is what we need to use for calculation of sigma nominal, W minus A into H, and in the numerator it's going to be load by, okay, W minus A into thickness. This will give you sigma nominal. Are you there? You remember this much? Are you
Yes, sir.
there?
Yes, sir.
Okay. So what we used to do is we used to take A and W, take the AW ratio, go to the required curve in our data handbook, travel upward till you touch the curve, then travel leftwards, we'll get the value of KT. Then sigma nominal is equal to P by W minus A into H. That will give you effectively the area of this actual portion only. So this sigma nominal, when you multiply it by Kt or K stress concentration factor, what do we get in that case? What do we get?
Maximum stress.
Maximum stress. Sigma max is what we used to get. Correct? So that is what is done here in case of plate with a hole. So now coming to the conclusion of that part is that it depends on mode of loading, type of stress used. For a circular in a hole in a white sheet, so normally KT is around 3. Okay. For biaxial tension, it's around 2. In shear, it is 4 based on maximum tension, and it's 2 based on maximum shear. These are the tentative values of stress concentration factor KT. Is that okay? Are you there? Okay.
Yes, sir.
So that is the value. So normally for plate withdrawal we have seen. So we normally get 2.76 around that value as the value of KT. Next, the elastic stress concentration factors are obtained. What all the various ways of obtaining this elastic stress concentration factors are: theory of elasticity, the numerical solutions like FEM, we can get the value of KT, experimental measures in that you have got brittle coating technique, and the most useful and practically viable technique is photoelasticity technique. Okay, and then you have got a strain gauge technique. So most popular is a photoelasticity technique to find out stress concentration factor in a member. You remember in your 7th semester of design lab, you would have done experiments in photoelasticity. Do you remember or you don't remember?
Yes, sir.
Yeah, you would have found out circular disc for which you would have found out the material fringe constant. Then for a rectangular bar with the 4-point bending, and then you would have found out circular disc, okay, with circular hole. You remember this specimen? So it is fixed in the photoelasticity apparatus, and load is applied from top, and we have found out the value of stress concentration factor Kt for this specimen. You remember? Do you remember in photoelastic technique you have done or you have not done?
We have done, sir.
Yes, sir. We have done that.
You have done. You remember, no? So that is
Yes, sir.
photoelasticity technique of finding out stress concentration factor. Of course, we can also find using finite element method. That's another easy way of finding out stress concentration factor. Next, SN approach for notched members is the next topic. Okay, that is, let's look at stress versus number of cycles approach for notched members. Notch, and again, notch means it can be hole, groove, keyway, stepped shaft, and whatever. Any geometrical discontinuity, they term it as notch. Okay, so please remember that. The effect of notch in the stress life approach is taken into account by modifying unnotched SN curve. This we have learnt already. That is modification of unnotched specimen with notched specimen. Then with notch sensitivity factor. Okay. So notched fatigue strength depends on these 4 parameters: notch stress concentration factor, notch radius, how big the notch is, what is the strength of the material, what is the mean and alternating stress level, that is SM and SA. Okay, so you remember Soderberg relation. Please remember Soderberg relation over here. What is Soderberg relation? KFT into sigma A divided by ABC into sigma endurance plus sigma mean by sigma Y. Okay, so it depends upon sigma A, sigma M. Okay, then the strength of the material, that is essentially what sigma Y we talk about in case of Soderberg relation. Then notch radius, what is the size of the notch, and the stress concentration factor KFT. We take no here KFT into sigma A. You remember Soderberg relation? Do you remember Soderberg relation?
Yes, sir.
Okay, so KFT is the stress concentration factor. Sigma A and sigma M are mean and alternating stress levels. Material strength is sigma Y, and the notch size, that is the 4th parameter. So these 4 parameters will give our notch fatigue strength depends upon these 4 parameters. concepts. Is it okay? Note down this first. Note down this. Finished, huh?
Yes, sir.
Noted? Noted?
Yes, sir.
Yeah. You remember this equation again? If you have done fatigue strength in your DME1, you remember this equation. You remember this equation or not? 1 plus in the fatigue strength of DME1 of 5th semester, you have this equation given by fatigue strength, okay, fatigue stress intensity, um, stress intensity factor fatigue, okay? Fatigue stress intensity factor is equal to 1 plus Q into theoretical form factor minus 1, okay? This Q is called notch sensitivity factor. So if not given, we used to take it as zero point 0.9, okay? So this is the notch sensitivity factor Q. So what is notch sensitivity factor is nothing but it is the degree to which the presence of notch would affect. Okay, so that is what is notch sensitivity factor Q. That is fatigue stress concentration factor Kf is equal to 1 plus 2 into theoretical stress concentration factor minus 1. So if not given, we are going to take it as 0.9 as the value of Q, which is essentially degree to which the notch will have effect on the fatigue strength of the component. Okay, this is what fatigue notch factor is all about, or notch sensitivity factor Q. This we have learned in our DME1 design for fatigue strength chapter number 3. Okay, and then comes the mean stress effects, okay, and Hayek diagrams. So what is mean stress effect? Again, we have learned in our previous discussions about mean stress effects. Okay, essentially the fatigue notch factor changes with mean stress effects and cycles to failure. So the Hayek diagram for 7075 aluminum alloy at 1 million cycles with and without notch was present. So this is the graph for notch specimen. This is for smooth specimen. And this dashed line NN, okay, NN corresponds to non-propagating cracks, which have often been observed in sharply notched parts. So this is the graph it gives, Hayek will give you. So here, the x-axis represents mean stress and y-axis represents the alternating stress. Okay, The points located on these are plus sy, minus sy, s dash y, then sf, okay, fatigue strength factor, sf, and then sigma f. These points will define the behavior of smooth parts. Okay, and then with the above diagram we can estimate what is the advantage of this above diagram is we can estimate the long life fatigue strength of parts with notches for any combination of mean and alternating stress. So this is the application of Higgs diagram. Okay, so what you do is note down this sketch for now. Note down the sketch. This is for smooth curve, notched specimen. This is mean stress, S dash y. This is where yielding. So notched specimen will have greater yielding compared to smooth specimen. You note it down as Higg diagram, H-I-G-H, Higg diagram for 7075 T6 aluminum alloy at 1 million cycles. Finished, huh? Finished? Yeah, Mithun.
Yes, sir. Yes, sir.
Now, to take this sketch now. Next, note down the sketch. Sy minus Sy, mean stress line, alternating stress, fatigue stress. Finished, huh? Finished?
Yes,
Yes,
sir.
sir.
Finished, huh?
Yes, sir.
Yes, sir.
So the last part of the module 3 was notches and their effects. So as usual, we know what is stress concentration, stress gradients, all these things we have learned in our undergraduate program only. And then we learned about Fortalis technique of finding out stress concentration factor, which we have learned in our design lab or 7th semester in design lab. And then notch sensitivity factor, we have learned in design for fatigue strength chapter, which is generally given by 1 plus q into kt minus 1. And mean stress effects is what we learned in our today, okay, which will give us estimation of long life fatigue strength of parts. That is given by essentially Heiger diagram, okay. So now I'll 1 second.